Hello, and welcome to the Quantum Innovator Series. I'm Chetan Nayak, Technical Fellow on the Quantum Hardware team here at Microsoft. In today's episode, we'll discuss the latest research and engineering advancements on our path to topological quantum computing. We'll also be taking you all on a behind-the-scenes tour of our quantum lab here in Redmond, Washington, so be sure to stick around for that. But first, let's talk about why we're pursuing topological quantum computing and how we're making progress towards our vision of quantum computing at scale. As always, our teams are in the chat ready to answer your questions. At Microsoft Azure Quantum, our mission is to accelerate scientific discovery by unlocking a new generation of hybrid quantum classical applications. Many of society's next big challenges, for example, creating more efficient batteries, are chemistry and material science problems. These problems are too complex for existing classical computers to help us solve. And that's why quantum is so appealing. In chemistry and material science, we need scaled quantum computers to simulate the interactions of complex molecules and atoms. When paired with AI and high-performance computing in the cloud, quantum will help us address challenges in areas like climate change, food security, and renewable energy. But quantum computation is a complex and delicate operation. As a result, the path to a quantum supercomputer will be similar to the path to today's classical supercomputers, in the sense that fundamental advances in the underlying technology will pave the road to such a quantum supercomputer. At Microsoft, we like to think about our industry's evolution to scale quantum computing in 3 levels. Together with our partners like Quantinuum and Atom Computing, we entered and continue to make significant progress in level 2, resilient quantum computing. When I look back at Microsoft's own quantum hardware journey, we've always been guided by the belief that scale quantum computers will help solve society's toughest problems. And that's why we've been building with an end vision of level 3 scale for nearly 2 decades. That involves taking a more difficult approach, namely, developing the world's first topological quantum system. A system that's built on hardware-protected qubits that have a degree of built-in error protection at the physical layer that doesn't entail painful sacrifices impacting the criteria, which I'll discuss momentarily. In the first season of the Quantum Innovator series, I shared more about this approach, so I won't go too deep here today. At a high level, topological qubits offer a path to scaling up with fast clock speeds, digital control, and more. In particular, those benefits include that these qubits are small. Each of our hardware-protected qubits will be less than 10 microns on a side, so you can fit 1 million of them in the area of a smart chip on a credit card, enabling a single module machine of practical size. They'll be fast. Each qubit operation will take less than 1 microsecond, so we can solve problems in weeks rather than decades or centuries. And they'll be controllable. This is really important and underappreciated. Our qubits will be controlled by digital voltage pulses, so we'll have a machine that doesn't have an excessive or unattainable input-output bandwidth. Today, I'm excited to talk to you about our most recent paper, which has been published in Nature, the world's leading peer-reviewed scientific journal. We explored a fundamental question. Could we do the information processing needed for a topological quantum computing system? Our team designed a way to perform fast, accurate measurements of the topological charge in real physical devices. In this paper, we demonstrate, yep, we can definitely perform this information processing. So let's break this down. Here's what our topological devices look like. Our devices have Majorana-0 modes, which enable the superconducting wire to accommodate either an even or odd number of electrons equally well with almost no discernible difference. And as a result, quantum information stored in this even or oddness is highly protected. That even or oddness, or parity, is associated with Majorana-0 modes, and that's also called topological charge. I'll use all 3 terms interchangeably. This builds on our previous paper published in Physical Review B, a journal of the American Physical Society. In last year's paper, we engineered a device in which we could controllably induce the topological phase of matter that gives rise to the Majorana-0 modes in which our qubit is encoded. This was necessary validation that our approach could work. It was a crucial first milestone in the path towards a scaled quantum computer. But that work left unresolved the challenge of actually processing information with topological devices. Our most recent paper addressed this as follows. We turn on a measurable difference between the even and odd states by coupling the wire to something called a quantum dot. This can be done with a digital switch. And when it's on, we can measure the topological charge accurately and quickly through its effect on the quantum dot. The way we use that is we use microwaves to detect the signature that the topological charge leaves on the quantum dot. And when the microwaves return from a circuit coupled to the quantum dot, they do so with an imprint of that topological quantum state. Our work shows that the electron parity of a nanowire say the difference between 1 million and 1,000,001 electrons, can be hidden from view by encoding it in a topological device, and then it can be made visible when we need to so that we can measure it out. Our results on this are in this plot in which you can see we're measuring the phase of the returning microwaves. Here we've collected many measurements together, which explains the scatter in those two blobs, with a spread that's determined by the noise in the microwave signal. Our work demonstrates a high signal-to-noise ratio, meaning a low error rate in parity measurement. Another way of saying that is those two blobs are much further apart than the spread that's in them. In other words, the measurement's reliable. We can confidently say that we've taken a significant step towards realizing a measurement-based topological quantum computing system. And this further opens up our path towards a utility-scale quantum computer. Now, this isn't a problem that was going to be solved just by more clever measurement, although that was important too. What it really required was design, materials, and fabrication innovation across the entire production chain, because this is something that had never been done before. And that's the reality of scientific discovery, of innovating and creating new solutions. You start with a hypothesis or a problem you're trying to solve, and then the discovery process actually teaches you what the true problem is, what it is that you really need to address. That's true for us here at Microsoft, and it's true for the countless companies we work with, trying to find new solutions for their industries and customers. As a scientist, this process of discovery is what drives me. It can be an arduous path, but I can honestly say that I do love it. So let's take a look at how we're solving the engineering problems facing us on the road to our topological quantum system here in Redmond. I'll hand it off to Patrick Codd, who runs the quantum systems team, and he'll be taking you behind the scenes in our lab.
Thank you, Chetan, and welcome back to our Quantum Innovator series. My name is Patrick Codd, and I run the quantum systems teams where we focus on readout and control of our qubit devices. I'd like to start our tour here by introducing John Watson. John, why don't you tell us about yourself and what you do here?
Yeah, so I lead our team, which works on developing on our qubit devices. Our team wears sort of two hats. Half of the team works on developing the procedures we use to tune up our devices and improve the materials that they're made from. And then the second half of the team works in the lab that you see here behind me, fabricating some of our control and readout hardware. And so the equipment that you can see here behind me is used to take starting wafers of something like silicon, and we build up different layers of material on top of that and successively pattern that to form circuits that we use in our experiments.
So John, tell us what's unique about this facility.
So this facility may look very similar to somebody who's familiar with the semiconductor industry, because many of the tools are common across both industries, but the materials and processes we use here are very unique. Specifically, we focus a lot with superconductors, which are materials which can carry an electric current without any resistance. In order to become a superconductor, though, they have to be cooled to very low temperatures, near absolute zero, which makes them kind of impractical for standard consumer electronics like a cell phone or laptop, for instance. But since our qubits have to operate at these low temperatures anyway, we can leverage a lot of the unique material properties that these superconductors have. For instance, the fact that these superconductors carry this current without any resistance allows us to make very high quality readout circuitry, which we use to measure the state of our qubits. Now, you can think of this a little bit as like the qubits are like little radio stations broadcasting their signal out to us. And if we were listening with sort of a normal radio with just normal metals in it, like copper or gold, we'd pick up maybe the few dozen stations that you would typically get in your radio at home. But by making these devices with superconductors, we can fit many, many more signals in. So imagine your radio, rather than picking up a few dozen radio stations, picking up thousands of stations. And this allows us to really scale up these systems to the many qubits that we need to solve useful problems.
Cool. Well, tell us then what makes you so passionate about this field and what excites you about quantum computing in general?
Yeah. Well, I think it's really exciting to be in this field at really such an early stage. And know that you're working on something that is really going to change the world. And on a more day-to-day basis, I think there's no shortage of kind of fresh problems to solve, and the work is very interdisciplinary. So it's fun, getting to interact with people coming from backgrounds in physics, material science, computer science, and learn from, in many cases, people who literally wrote the book on their respective area of expertise.
So John, we're in front of our clean room here. What goes on here? Can you describe it a little bit more?
Yeah, sure. So what you're looking at is, as you say, a clean room, and the reason it's called that is because the air in it is very, very clean and free of dust. The reason that we have to do our fabrication in a facility like this is that even the tiniest little speck of dust, if it's on the device that we're fabricating, will ruin it. So the air in here is actually substantially cleaner than you would find in an operating room, for instance. Up in the ceiling, we have these HEPA filters that filter the air that comes down. And then it goes through the holes in the floor and then gets recirculated back to the top. The yellow light that you see is because in the patterning process that we use to create our circuitry, some of the materials that we use in generating that pattern is sensitive to blue light or ultraviolet light, and so we have to sort of protect it from that, and then it'll go into our patterning tool, which actually shines a bright UV light to expose the pattern that we want. Then once we've written some pattern like that, we can either deposit some material on top of that and then stick the whole thing in a chemical, which will sort of wash away the remaining bits that weren't exposed, leaving, say, a metal wire on the wafer. Or you can stick that in some etch tool, for instance, which then will sort of etch away the material that was exposed, and then you can sort of rinse and repeat and build up multiple layers to build very complicated circuitry.
So, John, how does this lab and this facility in particular help us push forward in the field of topological computing?
So in this lab and in our program more generally, we're really right at this boundary between fundamental physics discoveries and the rigorous engineering that's required to build some useful technology. And so, this facility gives us a lot of flexibility that we can push the state of the art in terms of the components that we build, but also has enough reproducibility that we can start to build up more and more complicated systems. Personally, I find that a really exciting kind of juncture to work in, that we convert yesterday's breakthrough into tomorrow's sort of technological commodity that we can use to build up bigger and bigger systems.
Building a scalable system requires a multidisciplinary approach, I would imagine. How does that look for you and your team?
So our team has folks from a very wide variety of backgrounds. Some folks come from a low temperature physics background, others from nanofabrication, material science, electrical engineering. We kick off some new project, sort of consider what that's going to require from each team. And then it's really exciting to kind of see the projects progress and everyone coming at it from their different angles and thinking creatively how to solve these problems and move the ball forward for our program.
Cool. Well, we're going to go check out the rest of the lab. Thanks, John.
Sure.
So downstairs, John showed us the clean room where we fabricate our quantum devices. Upstairs here on the second floor, we have Ben Chapman here. Ben, please tell us a little bit about yourself.
Yeah, definitely. I work on our readout hardware, so designing and building the components that help us measure our quantum devices.
So if I look around this lab space up here, I see a lot of sophisticated equipment, a lot of cryogenic fridges. They're making a lot of noise. What goes on here?
The lab is where we measure all our new devices, new materials, come up with new ways to do control and readout. Basically, all the hardware gets tested in the lab.
Can you tell me a little bit about this fridge here and the chandelier?
Certainly, yeah. So this is a dilution refrigerator. It's a pretty standard instrument in the field, and it's something that we use to cool our quantum devices to extremely low temperatures. So what you're looking at, it's really amazing. This top plate of the fridge right here, that gets down to about the temperature of outer space. And as you go farther and further down, each one of these plates gets colder and colder until this very bottom zone is about 100 times colder than deep space. That's important for tuning up our quantum devices, but it's not enough. The other thing we need is a really large magnetic field, something like a few thousand times bigger than the magnetic field of the Earth. So when we're ready to cool down a new device, we'll attach it to this part of the fridge and then connect an electromagnet to one of these plates. That way we can get the device really cold and also immerse it in this large magnetic field. And then the rest of what you're looking at is really just electrical cabling to control that quantum device or measure it. One of the things I'll point out, which I think is pretty cool, these amplifiers up here, those were originally developed for radio astronomy. So they're extremely sensitive, work in really cold environments like this one. And now, instead of using them to listen to the stars, we get to use them to listen to our quantum devices.
Wow, very cool. I can imagine, though, as we scale these systems and we add more and more quantum devices into these systems, that the architecture might look different. Can you talk about that a little bit?
I mean, you can see just from looking at it that at some point, we're just going to have this fridge completely full with wires or cables. that really informs the way that we imagine these systems will look in the future. So one of the key themes and goals that we're driving towards is moving more of the control and readout hardware into the cryogenic environment. And that's really something that we use the fridge to test. And that's something that we're really excited about, because it just turns out that topological quantum computing is something that's really well suited for that kind of CMOS voltage control.
So when I think about traditional ASIC design, I know that traditional ASIC designers design around process corners, voltage variation, and temperatures. I would imagine in this case, the temperatures are completely different. Can you talk to me about that a little bit?
That's really something that informs the way we do the design. It's really critical that we modify that design flow to adapt to this new environment.
So basically a cryogenic PDK, as it were.
That's right, yeah.
Our approach to topological computing requires a multidisciplinary approach. Tell me what that means for you and your team.
To solve a problem this hard, we really need people with a wide range of different backgrounds and perspectives. And that's really something that you see in the team. You know, we have electrical engineers, mechanical engineers, software engineers, chemists, physicists. We have business leaders, we have product builders. We have people all over the globe. And you really need that because the problem is just so hard.
So Ben, why are you so passionate about this field? What drives you?
Oh, yeah. So for me, it's really about the enormity of the vision here. I feel like it's so fascinating. I get to work with the most talented people, and I just get to work on something that's much bigger than myself. It's how I imagine it would have been to be at NASA in the 60s or something, trying to put a person on the moon.
So Ben, thank you for spending precious time out of your day to explain what goes on in this lab.
Absolute pleasure.
I'd like to thank all of you for spending today with us in this tour of our facility here in Redmond with the Microsoft program. This is just a small snippet of the size and scale of our program. Our program actually exists among 5 sites in 3 different countries, and 3 of those 5 sites actually have a fleet of cryogenic fridges, just like what we showed you here today. As you can imagine, with all of these fridges, there's a lot of data, measurement that takes place, a lot of analysis that has to happen, a lot of visualization that takes place, and all of that happens in our control room. The control room brings together all of this data, all of this aggregate data from all around the world so that we can make sense of it and move the program forward. And now let's go back to Chetan.
Thank you so very much, Patrick, John, and Ben, for that amazing tour. And thank you all for joining us today for this behind-the-scenes tour of the Microsoft Quantum Labs. We look forward to sharing more updates with you in the future. Thank you, and see you soon.